In this video, we're going to talk about graphs of relations and functions. Remember that when we were solving equations in two variables, we said that our solutions would be the set of all ordered pairs that satisfy that equation, right? Well, since in a function as well as a relation is composed of a set of basic ordered pairs, then graphs are basically illustrations of all ordered pairs that once again satisfy the equation that gives the relation and the function. And so I have two relations here, y equals x squared and x equals y squared. Of course, there's a lot of different relations and functions that we can look at to graph, but you want to be able to graph any relation or function. I just chose these two as an example. Y equals x squared. Because we can solve for y and we can see that for every input x, we get one output, because if I square a number, I'm going to get a single output, then this is a function. We could also graph to see that by using our vertical line test, right? Well, let's go ahead and graph this. Now, I have a table of values. I have it kind of written long ways or wide ways here. Sometimes people, when they're graphing, they like to create a table of values, and they usually write their table of values with their x values here and your y values here, and you get your y values by plugging different numbers of x. Some good numbers to use, and we're going to see that these numbers don't always work for all functions, but just for now, since we're just getting started, we'll use these numbers here, -2, -1, 0, 1, and 2. So what we're going to do to get our y coordinate to our point, our ordered pairs that we're going to graph, we're just going to plug in these values, right? When we plug in -2, if we square that, we get 4. We get 1, 0, 1, and 4. And so we have a bunch of ordered pairs. We have the ordered pair -2, 4, the ordered pair -1, 1, the ordered pair 0, 0, the ordered pair 1, 1, and the ordered pair 2, 4. And so we can go to this space here to graph our function, which we already said that this is a function. -2, 4, that means from our origin, go left 2 and up 4. And there's our point. -1, 1, left 1, up 1. 0, 0 is there. 1, 1 is there, and 2, 4 is there. And now if we connect these points with a smooth curve, we get a graph that looks like that, right? And so here we have our graph is a parabola which opens upward. We have y is a function of x. And so that's some information that we know about this graph here. Now, if we go to x equals y squared, now this is solved for x and it's not solved for y. If we were to try to solve this for y, we would have to take the square root of both sides, right? I'm going to leave that there. I'm going to come over here and do this. So if I have x equals y squared and I try to solve for y, I take the square root of both sides. Remember, the square root of y squared, see, I'm so used to solving for x. The square root of y squared is actually the absolute value of x. And if we don't want to remember that it's the absolute value, we can just add on the plus or minus here to take care of the absolute value. And so we see that y equals plus or minus the square root of x. Well, with that, we have for one input x, for instance, if I input 1 in for x, well, the square root of 1 is 1, right? However, we have that plus or minus there, so it's going to be a positive 1 or a negative 1 as the output. Remember, when I input one value, I only want one output, so this is not a function, all right? So here we have y is not a function of x. We can check that by doing a graph, right? But how do we graph when we do stuff like this, right? One way to do this is to plug everything into solve the equation for y and then plug your x values in the normal way. Or since it's not y as a function of x, this is actually x as a function of y, right? Because if I choose one input value for y, when I square it, I'm going to have one output x, right? So here we have x as a function of y, right? Whenever you're a function of something, you can choose those to be your input values, right? So now I'm going to use -2, -1, 0, 1, and 2 for my y, and I'm going to plug that into my equation because x is a function of y. Plug in the y values, I should get 1x as my output, right? So if I square these, I'm going to get these values here. And so these will be our ordered pairs, right? Now, I got to be careful here. It's still 5 ordered pairs, but it may not look as nice as the other graph, right? So let's go ahead and graph these, right? I have the point 4, -2. So I go right 4 and down 2. I have a point. I have the point 1, -1. So right 1 and down 1. I have the point 0, 0. I have the point 1, 1. And I have the point 4, 2. And as we can see, if I connect these, yeah, I'm gonna just do this. That should be a little curvy and less V looking and more U-ish. But I get a graph that looks something like that. And as we can see, that does not pass the vertical line test. It is actually a parabola that's opening to the right. All right, so if I wanted to put some information about this graph, it's a parabola opening to the right. We have y is not a function of x. In fact, we have x is a function of y. All right. Now, what I want to do is I want to be able to also find the domain and range while we're looking at the graph. And so if I go to this graph to the left here, my domain is your set of all x values that are x coordinates to these points on your graph. Notice this extends indefinitely to the left. This extends indefinitely to the right. So when I'm thinking about my x-axis, all of my values are going to be x coordinates to my point, right? So my domain, which I'm going to abbreviate with D, is going to be from -infinity to infinity. My range is the set of all y values where my function is defined, right? Notice that none of my graph of this function has y coordinates that are negative. All the y coordinates to the points on my graph are positive, are above the x-axis, and even on the x-axis. In fact, the lowest y value I have is at this point here, which is the origin, and it has a y value of 0. So I'm going to put a bracket because I include that 0. And since my function continues to go up indefinitely, I'm going to go all the way to infinity. All right. When I look at this graph over here, when I'm thinking about my domain, notice it's kind of the opposite here, right? There are no points that have negative y values, right? And so if I go from left to right, my leftmost point on my graph is the origin, and it has an x coordinate of 0, and that's included because that's a point on that graph. And all of the x values all the way to infinity are x coordinates to the points on my graph. And so I have the domain of 0 to infinity. And then my range, now I start thinking about my y values to these points on my graph. It extends indefinitely going down there. This one goes up. And so my range here would be -infinity to infinity. Now, I've looked at a graph that has a function, which is here. And I looked at a graph that's not a function, which is here. So I want you to be able to graph a relation and a function, and a relation that's not a function and a relation that is a function by graphing. And then you should also be able to find the domain and range from the graph. All right. But graphs gives us a general representation of what these things look like. All right. Example 2 here is the equation of a circle, a function or a relation, right? Or just a relation. We know that a function is a special relation, but is it a relation? Is it just a relation, or is it a relation and a function? I guess that should be a better question. All right. Well, we know that it's not a function, right? Because the equation of a circle is this purple. This is an example of one. Is this purple or pinkish shaded or figure here. And we can tell that it does not pass the vertical line test, right? And so we're going to say no because it does not pass the vertical line test. All right, so we know that it's not a function, right? However, if I were to just look at part of this circle, right? Just part of the circle, for instance, just half of the circle. So let's say I just looked at half of my circle here and didn't worry about the part of my circle that was under this line and just focus on the top circle or the semicircle, the top half semicircle. then that would pass the vertical line test, right? Or if I just looked at the bottom half of the circle or the lower semicircle, then I would also have a function, right? And notice if I look at the semicircle, it encompasses the entire domain of that circle. So I can get a picture of the entire domain, right? Because my domain of this circle goes from this left end point to this point over here, right? Well, if I take the bottom half of my circle away, my domain is still going to be the same. So I get a good representation of my circle still. And so sometimes instead of looking at a full circle, sometimes we want to look at a semicircle or semicircle in order for us to use it in a way that we use functions. All right. And so what I want to do is I want to adjust the equation of a circle, right? The equation of a circle, which you have memorized, is this right here, right? We could see by solving for y, we can tell that this is not a function. If we solve for y here, for instance, we get r squared minus x minus h quantity squared. We have to undo that square, so we're going to take the square root of both sides. And when we take the square root of both sides, we have to remember to put on a plus or minus. Once we see a plus or minus in an equation, we know that it is not a function. All right, I don't care which side the plus or minus is on. All right, I'm going to continue to solve for y by adding k to both sides. And so we get that our semicircles, all right, the top half of your semicircle is going to be given by the plus. So y equals k plus the square root of r squared minus x minus h quantity squared. And then the bottom half is going to be given by y equals k minus the square root of r squared minus x minus h quantity squared, right? So this is the top half of your circle, and this is the bottom half, right? The difference lies within that plus or minus there, right? That is the main difference. All right, and so we could use the equation of a circle. When we solve for y, we see that it is not a function, but we can make it a function by separating it and only using either the top or the bottom half, right? And so some people say, oh, you should memorize the equation of a semicircle. Well, if you know how to solve this equation for your variable y, then you don't have to memorize another circle, right? You just have to be able to solve that equation, right? Remember, this is your x coordinate to your center. This is your y coordinate to your center. And this is your radius. R equals your radius, but it's sitting there squared, right? So r squared is your radius squared, right? So if I want to sketch the graph of a semicircle, it would look like an equation like this, right? Now, this equation doesn't have this full form here of one of these two equations here. So I want you to look at this carefully. It has the form, but it doesn't have all of the pieces. For instance, there is no number in the place of k, right? So I'm going to try to write this to look like that equation there, right? So here I have no k. Right? So that means my k is 0. Now, if this is a plus sign, then I know I have the top half of a circle right before my square root, right? If it's a minus before my square root, I know I have the bottom half. Well, there's a minus in front of my square root, so I have that there. And then I have my r squared. Well, r squared, in order for me to square 9, I have to get 3, right? I have to square 3 to get 9, right? And then I have a minus, right? This always has a minus after the r squared, so here and here. And then we have an x minus h quantity squared in both of these, right? Well, here I just have an x squared. That just means there's a 0 that's being subtracted and squaring, right? So since the h was always your x coordinate of your center, the k was always your y coordinate of your center, we know that this is a semicircle. The center is at the point 0, 0. And the radius, your radius squared is sitting up there as 9. I wrote it as 3 squared. So your radius is 3. All right. And I know that this is the bottom half of a semicircle. So our bottom half of a circle. All right. So if I want to draw this graph here, then all I have to do is go to my origin and plot my center. All right, now your center is not an actual point on your graph. It's just a feature of a semicircle, right? The actual points on your graph are the values that make the actual semicircle. So we have a bottom half of your circle, right? That means if I go down from my center, my radius number of units, so go down 1, 2, 3 units, I'll be on my graph. If I go to the right 3 units, I'll be on my graph. And if I go left 3 units, I'll be on my graph. Now, it's harder to go diagonally, so that's why I'm not doing that. But as long as I can draw a good sketch of a graph that looks maybe like a semicircle, then there we have our graph, right? So this is the graph of my semicircle, which is y equals negative square root of 9 minus x squared. So that's what the graph looks like. Remember, your center is nothing but a feature of your semicircle. These are the coordinates that satisfy your semicircle, right? You put 0, 0 in here, you're not going to get something that's correct, right? Because center is a feature, not a actual point on your graph. All right, so be able to not only graph relations and functions, but sometimes we can turn a relation into a function by only looking at part of the graph of that relation, all right? And that is what we did in this example here. All right, let's go to other ways that we can make functions a little more complicated, actually. We're going to talk about piecewise functions, right? Piecewise functions are functions in which different formulas are used for different regions in the domain. By the way, let's go back and let's find the domain and range of this semicircle, right? Because we want to get in the habit of being able to look at a graph and finding the domain and range, right? I'm going to find a domain and I want to find a range. You should actually pause the video and find them and then see if you got the right answer as I'm going to write it here. Pause. So our domain is from -3 to 3. All of our x coordinates between this endpoint here, all of my x coordinates all the way until I get to here are used as x coordinates on my graph, right? And then my range, my lowest y value is -3, and I go all the way up till I get to the y value of these 2 points here, which are 0. And since these points are actually on my graph, I have those closed circles, I use brackets around all of that. Now, these piecewise functions are functions in which different formulas are used for different regions in your domain. There are some applications where you calculate different things for different values of things. For instance, the tax framework, when you pay your income taxes or whatever, depending on how much money you make, when you make between 0 and certain thousands of dollars, then you're going to calculate your tax rate at this percentage. And then the amount that's over that top part to another couple $100,000, your tax rate is going to be calculated differently. And so we're using different numbers or different calculations based off of different input values. That's what piecewise functions are. Of course, we're going to be very algebraic in this class, and so we're going to look at piecewise functions that are made up of things like this. All right, so it says let f of x equals, and then I have two formulas of what we call functions here, right? The square root of x is a function because if I plug in one x value into my square root, I'm only going to get one output, right? When you plug in a square root of, take a square root of a number in your calculator, you're only going to get one output, right? The same thing, it happens to negative x. That's linear. You plug in the x value, you're going to get one output y value, right? And not only do we specify the formulas, but we also specify what part of your domain that formula aligns with. For instance, the square root function aligns with x values that are greater than or equal to 1, and then this function aligns with x values that are less than 1. And so just so that we get used to this, I have a couple of things we want to evaluate. All right, I want to find f of -2, right? Well, if I want to find f of -2, I got to figure out which part of the domain. Well, -2 is definitely less than 1. So if I want to find out what f of -2 is, I've got to replace this x with the -2. So that'd be a -2, which is a +2, right? And then we can do this for f of -1. Again, I got to go to the second function here because -1 is less than 1. And so that's a 1. F of 0, go to 0 is less than 1, so I'll plug it in there. F of 1, 1 is greater than or equal to 1. Because this has an equal to, now I go to my square root function and I have to plug in the 1 there. So the square root of 1 is 1. notice here I jumped to 4. I could have done f of 2, right? I did -2, -1, 0, 1. If I did f of 2, then I would do the square root of 2, which is an irrational number. And because we're going to graph next, I tried to use whole numbers here. Now, you can always plug in 2, you can always plug in 3. I just chose numbers that if I plug it into my square root function, I'm going to get an integer output, okay? That's why I chose these values here. So f of 4, I know the square root of 4 is 2, and I did f of 9. That's my next perfect square. Uh-oh. That was supposed to be a 9, right? And I get 3. All right. And so basically what I've done here is I've just basically obtained a bunch of ordered pairs, right? I plugged in these x values into my piecewise function, and I got these output values, right? So this is just a different way to write that. And now I have a bunch of ordered pairs. All right. So notice how we write things sometimes differently, but we're doing the exact same thing. Remember, when you evaluate a function, you're just finding a y coordinate, right? Because y is a function of x. X is your first coordinate, y is your second coordinate. You get the output, you get your second coordinate, right? And so now that I have these ordered pairs, I am going to graph this function. My first point was the point -2, 2. So I'll go left 2 and up 2. I had -1, 1, 0, 0, 1, 1. All right. Now I need to notice something. I'm going to go ahead and plot the other points, right? 4, 2, 9, 3. Now, part of my function is supposed to have the behavior of this function right here. In fact, so that I can see this and talk about it, let's do this, right? So when I graph a piecewise function, I want to make sure that I obtain the actual behavior of both of these functions here. So I'm going to graph the values that were related to this line, x equals negative, y equals -x, right? That came from plugging in all of the values that are less than 1. So these values here, right? I'm actually going to graph that part in orange so that it can actually come up. And so I'm going to graph that line. Uh-oh. It should be a straight line that looks more like that. I am so sorry. But we get a graph that looks like that. Bear with me. We get a graph that looks like that, right? It is a line. When I do the square root of x for x values that are greater than or equal to 1, then it's sort of a curvy graph. It's a very curvy graph. So when I do this, I actually have and then at 1, I know I have a closed circle. So I'm going to close this in because the square root function started at x equals 1. I plugged in 1 and I got a y value of 1, okay? That's what we did in this chart here. We plugged in 1 to the square root of 1. We got 1 as our output. Now, if I look at that, I actually have a gap, all right? If you just look at x values less than 1, all right, it's almost like this. What we did was we plugged in -2, -1, and 0 into that graph, and then and that table, and then the other one we plugged in 1, 4, and 9. I have a problem with this. It doesn't tell me there are some values that are between 0 and 1, and when I just do my graph or my charts with just -2, -1, and 0, and I stop at 0, I don't know what happens for these values that are between 0 and 1. I have a gap here, and that is not correct. And so what I tell my students, and they always forget, so please don't forget, is even though I'm doing a table like this, I'm going to also evaluate my function at x equals 1, and I'm going to plug it into this one as well. All right, that's when I'm going to graph. Now, this point is not included because I know that at x equals 1, my functional value is the square root of 1, which is 1. But so that I can alleviate me from having the graph so that I know what happens between 0 and 1, I need to plug it into this function here, y equals negative x. So plug in 1, I get negative 1. But what I'm going to do is I'm going to put an open circle to let everyone know who's reading my graph that this point is not included. The functional value at x equals 1 is actually coming from this function here. And so when I draw my graph, it's an open circle, but it should still be a line attached to this line, right? Because if I put 0.5 in there, I should get negative 0.5, right? So I need to see that on this graph here. If I don't do that, then my graph is not complete. All right, now that we have that, we can find our domain and range. Our domain is going to be our set of our x values where our function is defined. These values over this part of my function here has x values that are less than 1, but at 1 and greater, we have this part of my function, right? And so since that encompasses all of my x values, it's going to be from negative infinity to infinity. All right, our range encompasses all of our x value, all of our y values where our function is defined. And this is a good one here, right? So starting from bottom to top, my lowest point on my graph is the open circle at y equals negative 1, right? It's an open circle. So I'm going to use a parenthesis. I'm going to do negative 1. And I'm going to continue indefinitely upward in this part of my function and upward in that part of my function, right? So it's going to be from negative 1 to infinity. Notice here I use a parenthesis because this is an open circle. This point isn't included because if it were included, I wouldn't have a function because I wouldn't pass the vertical line test. All right. And so what a lot of people like to do when they're given a problem like this is they like to do a table of values, do two separate table of values. That's actually what I do. In my first table, I choose x values that are less than 1, and I try to look at the function, right? So I'm going to do like 1, and I know that this is less than, right? But I need to include that value. I always put a note to say don't include or not included, or I'll put open to remind myself to do an open circle when I plot this point, right? So 1, 0, negative 1, and negative 2 are values that are less than 1, and I'm including this 1 so that I know I won't have that gap in my graph, right? And then my other table, so that's the y equals negative x, and then my other table is going to be coming from y equals the square root of x, right? And so that's for values that are greater than or equal to 1. So like 1, I can use values like 2, 3, but I'm going to use whole numbers, and then I'll put those in my table. And just so that you are clear, you can put the word or remind yourself that that is going to be closed. All right. I mean, you just plug your points in and you get your points on your graph. All right. So that is an option, but be able to graph piecewise functions. Sometimes they come up. The last thing we're going to talk about is are some graphical properties. And that has to do with, it actually has to do with your average rate of change and your difference quotient, but we're not going to make that connection here. We'll wait till next semester or wait till when you get in calculus to make that connection, right? But these are 3 words that we can describe your function or intervals of parts of your graphs of your functions, right? So these are some graphical properties. A function is increasing if it looks like this, right? So this function is completely increasing. There are sometimes we'll have functions that may increase, decrease, increase, decrease, things of that nature like that, right? Now we want to make sure it is a function, but sometimes they do things like that. And so we can find the intervals where they're increasing, but this function is completely increasing, right? It says as x increases, f of x also increases. All right. In more technical terms, if x sub 1 is less than x sub 2, right? So you have 2 input values. Since they're x coordinates, we're going to label them x1 and x2, right? Like in this picture, this is x1 here, that is x2. x1 is to the left of x2, so x1 is less than x2. Then if your function is increasing, then the y value at your left point is smaller than the y value at your right point, right? So that means f of x1 is less than f of x2. And as we can see, those when we're looking at the y values, your first y value is definitely less than your second y value. So that means your function is increasing. When your function is decreasing, it looks like this. It's going down, right? So as x values increases, your f of x or your y values decreases. And so in more technical terms, again, if x1 is less than x2, if your function is decreasing, then the functional value at x1, or the y value, is smaller than the functional value at x2, all right? And then you can use the word constant. As x increases, f of x is constant. It stays the same. And so if you have two input values, again, x1 is less than x2, then the functional values are actually equal on that interval between x1 and x2. All right. And so we should be able to look at your graph to determine where your function is increasing, decreasing, and constant. And we're also going to state the domain and range of each of these functions here. All right. So let's look at, we're just going to look at one of these. Let's see how much time. Oh, we're running long. We're going to look at one of these. Let's look at this example here, right? We have a semicircle here. It says to state the domain. Our domain runs from -4 to 4, and our range runs from 0 to, this is counting by 2. That's 4. It's not labeled. But our range is our lowest y value to our highest y value. There we go. Our function is increasing, right? So it's increasing from here to here, right? From this point right here to this point right here. By the way, when we write intervals where our function is increasing, we usually use these closed intervals, and we do create our intervals with respect to x. So this point has the x value of -4. And this point is the last point where it looks like it's increasing, and that has an x coordinate of 0. So it's increasing from -4 to 0. And then the other part of my graph, from here to here, my function is decreasing. All right, this point has the x value of 0, and then it has a y, the other point has the x value of 4. All right, there are no intervals where my function is constant, and so I'm going to say not applicable. All right. Notice I'm using closed intervals because we have to include the points, 2 points where your function, in order to satisfy this definition here. It says if x1 is less than x2, well, -4 is less than -3.999, right? And so -4 has to be in this interval, which is why we're using these closed intervals here, right? So when we write increasing and decreasing, we usually write them using both sides closed, all right? Unless we want to know, unless our function continues indefinitely with infinity or negative infinity, and we always put those with parentheses. All right, that concludes this video. I'll see you next time.